Trying to close some other stuff out too, because I know this computer is slow. If there's too many things running at once. All right. Uh, that's coming up. So we've talked about protecting groups, and again, the whole purpose or the goal of using a protecting group in a synthesis is to keep certain functional groups from reacting, right? You don't sometimes you'll have a synthesis of a molecule that might have a bunch of different functional groups in it. You don't want those functional groups to actually like react and give you some product or some unexpected or undesired product. So sometimes you have to protect those functional groups. Mostly you'll use protecting groups on amines, alcohols, and then sometimes you'll use them on carbonyls also. So these are some basic silo protecting groups. You don't have to, all this is, you'll have it. I have already uploaded a document with all these in it, so don't worry about trying to scribble them down or whatever. But some of your basic silo protecting groups here, like TMS, trimethylsilo, that's like one of the simplest and easiest ones to apply as well as remove, right? And we talked about some of these the other day, tert-butyl dimethylsilo, tert-butyl diphenylsilo. So all of these different protecting groups and the silo protecting groups, you put them on based on uh, how robust they are, right? If you have a TMS group on, that's going to come off pretty easily in the presence of a weak acid. So if you need something more robust, then you use some different silo protecting group, right? Something bigger that's harder to remove, like the TBS or the TES or the TBDPS, so like that. You can also use TIPS, triisopropyl silo. You can see that up here in the top uh, right corner, right? And then you can also use, depending on what, again, uh, what your goal is and how robust you need that protecting group to be. That's going to determine which one of these you use, right? So down here is the basic application, like how you put it on. Normally you use a silo chloride or a silo triflate in the presence of which are alcohol and some weak base like imidazole or 2,6-lutadiene, right? One of those two bases. Sometimes you can use DMAP, dimethyl aminopyridine, and then again, it's a very simple process. You take the alcohol, you add in the base, you stir, probably somewhere like 0 degrees, not really low temperature, but below room temperature, because some of these reactions are exothermic. And you react that alcohol with your silo chloride or your silo triflate, and it's a very facile reaction. And one of the pluses is that the oxygen silicon bond is very strong, right? So the driving force is to make that strong OSI bond, right? So it's a very easy reaction to do, right? So the way you take these silo groups off is to treat them with some type of acid, right? Normally you use hydrofluoric acid. You can use that to deprotect silo groups. Uh, but the stability, again, depends on the type of group. And you can see here where it says TMS, and general stability of silo ethers towards acidic media increases like so. So for TMS, that's the weakest silo protecting group, the easiest to remove. You go to TES, you can see it's 64 times more stable or less easy to remove. And then you go to TBS, it's 20,000 times harder to remove, so on and so forth. So depending on what your goal is and how robust you need that group to be, that's going to determine which one of those groups you pick uh, to protect your alcohol. So normally your silo groups are used to protect alcohols. And on the chart over here, you can see how the TBS, TBDPS, diphenyl, isopropyl, all these different silo groups, you can see the half life for the removal of that group increases uh, with the size and the different functionality on silicon, right? So you can see what you compare TBS and TBDPS right here. Hopefully you can see that cursor. Uh, you see that the half life is 140 hours in tetrabutyl ammonium fluoride, and then 375 hours in the same with the same deprotecting agent, right? 375 hours for the TBDPS, right? And then you can look over here in hydrochloric acid, 1.4 hours, and then this is uh, the half life is greater than 200 hours for the TBDPS. So these are really good protecting groups. And again, you when you're doing a total synthesis, you have to strategize about your protecting groups because sometimes you may want one alcohol to be exposed while the other one is protected. So you have to vary your protecting groups, and that way you can strategically remove them when you need to remove them, right? And you can see up here on the basic conditions, you can also this is 5% sodium hydroxide, 95% methanol. TMS comes off in less than a minute. And then the isobutyl dimethyl group, 2.5 minutes, so on and so forth. So you can see the larger the group is, and the more functionality it contains on the silicon, then the harder it is to take it off, right? So here's a just an example of a monoprotection. And again, you want this to be selective because sometimes if you have a large molecule with a lot of alcohols in it and a lot of your natural products have free alcohols, you want to be able to protect those groups selectively. Right. So in this particular case, uh, you can do monosacchylation of symmetrical diodes. And you've seen up top, you treat it with sodium hydride, and then you add TBS chloride, and one of those alcohols gets protected over the other. And again, very facile, very efficient reaction, 75 to 97% yield. Um, Same here with TBDPS chloride and diisopropyl ethylamine. That's your base. You always need a base because you have to deprotonate the OH group so that it's a better nucleophile because it's going to attack silicon and kick off whatever leaving group is on silicon. So it's doing like a substitution on silicon. Uh, Again, that's selective, 75 to 86% yield. And then you can see on the bottom with butyllithium as the base, you can selectively protect one alcohol over the other, 88% yield. That was done by Roush. And again, these are old methods, but they are tested and they work. All right. So what happens here in this monster of a molecule, you can see, I don't think yeah, I didn't do that. You can see, hopefully, can you see my cursor moving around on the screen?
Yes.
Okay, cool. So you can see right here, this is, if you look here, you actually have two free alcohols, a secondary alcohol here and a primary alcohol here. And if you wanted to protect the primary, you can see even in this molecule, there are some protecting groups already in place. There's a TIPS group, triisopropyl silyl group here. There's a triethyl silyl group here. Um, so there's some alcohols that are already protected. So treating this molecule, right, all everything else here in here is inert to silyl protection. You would think that the carboxylic acid would be available, but those electrons are tied up in resonance, so you don't really get any competition from that. But your alcohol right here, you can treat it with uh, TES chloride, 2,6-lutadine, and you do. Once again, the selectivity is gonna also kind of be dependent on the temperature. Like at low temperature, if you got a competitive process, the lowest energy process is probably gonna be uh, faster. That's gonna be your kinetic product, right? And if you look at this secondary alcohol, it's really like sterically encumbered. It's got a lot of groups around it compared to this a primary alcohol, which is not so sterically hindered. And so that's probably where your rate difference for that the oxygen reacting with silicon comes in at. The fact that this one is a little bit more bulky and harder to get to, plus at low temperature, there's not the energy difference, the gap between one alcohol reacting and the other is probably a little bit bigger. Um, so yeah, so this alcohol is selectively protected here in the product, and you can see that right here, right? And eventually, you can see that the molecule is cyclized. This is forboxazole B. You can see, and this was done by David Evans, and this was in 2000. You can see that the molecule was eventually cyclized here, right? Between here and where the carboxylic acid is, you can see that OH. That's the reason why I needed that one free, right? And not this one, because you can easily see that if this alcohol and this alcohol are both free to do a condensation with this carboxylic acid and esterified, this one's probably going to react much faster because it's closer in proximity, right? But you need this protected so that when you get ready to do the esterification and the ring closure, then you're not hamstrung by competitive processes. Because you can imagine a natural product with this many stereo centers and this much complexity. If you get out the corresponding ring where this hydroxyl cyclizes, that's going to be a mess, and you may or may not be able to separate them. Right, so that's one instance where this selective protection has some utility. Here's another uh, instance. This is by Holton. This is in 1994 in Jax, right? And so this is a selective deprotection, right? And so all of what this backbone is, this is the backbone for Taxol, which is an anti-cancer drug, and it's been a hot commodity for total synthesis for synthetic organic chemists for decades, right? Once it was first synthesized, I think it back in like 90, it was like 92, I think, or 91. Holtman and Holton in at Florida State, and then E.J. Corey, I think, synthesized this. No, I'm sorry, Casey Nicolau synthesized it. So you had these two groups competing to see who could synthesize it the fastest and the most efficient. But you can see right here, if you look at the product, you have an acetate protecting group here. You can see that this is a protected diol. We're going to talk about that too, because you can protect a diol with like a acetone or an anhydride to generate this carbonate right here. You can see you have a bond protecting group here, which we're going to talk about shortly, and then a TBS protecting group here. And over here is really important, right? You look at the order. You have a TBS, you have a bomb, which you have to take off with a totally different set of reagents, an acetate, which you could take off with a totally different set of reagents, and then this carbonate. Again, that requires a different set of reagents to remove that. And this is all strategic, right? If all your protecting groups came off with the same deprotection agent, then that would be bad, right? So the you can see here you want to selectively remove the TES, right, to give you this free alcohol right here, and eventually that was protected with a as an acetate, right? But when you have a total synthesis like this, and you have lots of different functional groups that are reactive, then you have to be really selective about how you apply your protecting groups. All right, so these are some other carbonate and ester protecting groups. So you can see you have your acetate protecting group, chloroacetate, dichloroacetate, so on and so forth. TFA, pivalate, which is a really a robust protecting group. You can see that big tert-butyl group here. You have your benzoate protecting group, and then methyl benzoate, and so you have a bunch of different carbonyl protecting groups as well, right? And most of these are applied using some type of esterification with an acid chloride. And then you have the allocarbonate or alloc and FMOC. These are really popular as well. Um, and then these are just some other really popular and highly used protecting groups. The TROC group, TOC, CBZ, BOC. You see this BOC a lot, especially if you're doing any type of amine chemistry. BOC groups are very popular in protecting amines, as well as I think it was on the other page. This FMOC group, that's another group that you'll see a lot when you're trying to protect an amine, right? And then so here, this is the methodology for attaching them. Again, you can start with an acid chloride plus your alcohol with pyridine and DMAP. You can do an anhydride with your alcohol and pyridine and DMAP, or with the acid chloride, the base is not necessary. You just use pyridine. Uh, Let me take that back. The DMAP is not necessary. DMAP is more. Sometimes it acts as a catalyst, but you don't need DMAP with the acid chloride because with it's really your acid. This is I'm sorry, chloroformate. That's what this is. The acid chloride is here. This is the chloroformate. You don't need the DMAP with that because this is a really fast reaction, right? The DMAP actually, what that does with an acid chloride is it actually displaces the chloride, right? You do an addition followed by an elimination, and then the alcohol comes in and does the same thing and displaces DMAP. Um, and this is the structure of DMAP down here. And so this is what the intermediate looks like. So the pyridine nitrogen here is what displaces your acid chloride. And then so this is your intermediate, which is more reactive because it's charged, and that's where your alcohol is going to attack the carbonyl carbon here, right? Um, so that's why the DMAP is added to these two reactions. But for the chloroformates, those are highly reactive, so you don't have to worry about adding in DMAP. All right. So this is the susceptibility of your esters to hydrolysis, right? Because again, these don't come off with acid uh, removal. They are based. They're hydrolyzed by adding base to remove them, right? So this is the pivolate, and then you have the let me go back, methoxybenzoate, followed by the benzoate, so on and so forth. So you can see what the I guess the nature in which they come off or how facile they are at being removed. You can see that the pivolate is the easiest to remove, and then as you go down, the trifluoro methyl acetate is the hardest, right, to remove as far as when these are bound to an alcohol as a protecting group, and you're trying to remove them with by hydrolyzing them with the base. All right. So this is a selective removal, and you can see here that this is a enzyme catalyzed removal with acetylcholinesterase, and you can selectively remove one of the acetate protecting groups while not touching the other one. So you can see that right here. And just to show the utility of it, they took the Deardorff group took this alcohol that was unprotected, and they just oxidized it up with PCC. All right, same thing here. This is also uh, enzyme catalyzed, and so you can see here you can remove this acetate protecting group with a lipase and get the free alcohol here, right? And you can see up here, this is important too. It says 99% EE. because there is no diminution in the stereochemistry, because these are both uh, well, these are both chiral centers. But once you um, add the enzyme, right, this is symmetrical, so the chirality is going to be non-existent. But once you convert it to the alcohol, then this is chiral because the symmetry is gone, right? So that's 99% EE. And let me go back to here, right? So you have a tin oxide, dibutyl tin oxide here to form this tin complex, and then you can selectively isolate one of those oxygens, the primary over the secondary, which is the product of which is shown here. And this is in a review paper by Hanessian and Tetrahedron in 1985. So, but again, the date and the age of these methods may seem like, oh wow, 1985 is a long time ago, but people still use these are still methods that are employed like all the time. Protecting group chemistry is very important to an organic chemist who's doing total syntheses. Very important. And again, right here you can see the selective removal of the chloroester here to give you this alcohol in the presence of an epoxide, and also in the presence of this diol that's also protected as an acetal, and another epoxide here. So this again, it's a mild method, but it's selective for only the chloroester right here, right? And so you can see that that alcohol is now deprotected, and you get the deprotected alcohol in 71% yield without any uh, reactivity of any of your other functional groups. All right. So here's another deprotection method. This was done by Andy Myers. I'm sorry, that's not Andy Myers, but by the Myers group. I looked at the date. I apologize for that. Myers is much younger than that. But this is by the Myers group in 1978, and it's a way to remove the carbonate protecting group. So if you have your alcohol protected as a carbonate, a particularly methyl carbonate, then if you treat this with potassium carbonate and methanol, you can get the free alcohol. If you have it protected as an FMOC, then you just treat it with base, triethylamine and pyridine, and you can free up that alcohol, right? Um, if you treat this with the trichloroester, you can treat it with zinc and acetic acid and remove it. And again, all of these removal methods are very important because the removal method has to also be uh, strategically applied so that some other side reaction is not happening on your larger molecule, right? So you can remove the allocarbonate using palladium DBA, uh, probably a catalytic cycle, a catalytic method here to remove that. And then again, you can look at here. Here's another way to remove the carbonate. It's a silicon substituted carbonate, so you use TBAF in this case, tetrabutyl ammonium fluoride, and do that in THF. All right. Any questions so far? I think the objective or the main objective is to understand why protection and deprotection is even necessary. And the reason it's necessary again is because sometimes you're doing a total synthesis and you need certain functional groups not to react when you're doing a reaction that you know that they're susceptible to. Right. All right. So here's another class of protecting groups. So we looked at esters protecting groups, silo protecting groups. So here, these are ether type protecting groups. So they convert your alcohol, your free alcohol, into an ether, right? So some of the more important and the more widely used ones are here: the MOM ether, methoxymethyl ether, the BOM group, benzoyloxy methyl ether. THP is also another one that's pretty widely used, and then the MEM 2 methoxy ethoxymethyl ether. This is also one that's heavily used. And the general method for adding them is the there's an alkyl halide substituent somewhere on that ether that can be used as an electrophile. So you use that type of substitution pattern on that ether and react it with an alcohol in the presence of a base, right? So it's like a Williamson type ether synthesis, all right? And you can see here the solvent combinations usually use like DIEA and then methylene chloride, or and then sodium hydride and THF, or sodium hydride and DMF as your base and your solvent. So it just depends on what you're trying to do, and it depends on which one of these protecting groups you're using, right? But the basic method is to take the alcohol and treat it with this functionalized ether that has some type of leaving group attached. So you can do a like a Williamson type ether synthesis. And to remove them, lots of different methods. You can use concentrated HCl. Again, if you do that method, you got to be certain that there are other groups, other functional groups in your molecule that are not susceptible to acid hydrolysis. You can use a bromocatechol borane, and you can cleave a bunch of these. You can take the mom, the mem, the diterbutyl, and the benzoyl ether off with the bromocatechol borane reagent, right? And this is really important. Again, everything is strategic. You have a strategy for removing or adding protecting groups. Uh, and then you can use lithium tetrafluoroborate also to remove certain ether protecting groups. Right. Same here with benzoyl methyl ethers or bomb ethers. You use sodium and ammonia, and anytime you see sodium and ammonia together, uh, you know that is a one electron process. So it's like a radical mechanism to remove that bomb ether. You can hydrogenate it off with hydrogen gas and palladium on carbon, and you can also use this Diodes reagent. It's like an ion exchange resin. You can use that, and that'll also remove the bomb ether, BOM ether. I don't know when my Zoom got downgraded. I'm kind of mad about that, low key. Uh, another way to remove the benzoyl methyl ether is to use DDQ, which is also works via a radical mechanism. So it's like a one electron. It's a good source of a one. It's a one electron donor. So DDQ is a way to remove this ether as well. So a lot of times, if we're reading a paper and we see some of these reagents, then we'll know like what the purpose of those reagents are, right? And this class of protecting agents is for diodes, right? There's a lot of different ways to protect diodes, but the probably the easiest way is to convert a diol into an acetal, right? So you can have 1,2 or 1,3 diols, and both these methods work for both. You can see that you can do a ethylidene acetal. You can do a acetonide, which is here, and then that's just treating the diol with acetone. You can do a cyclo pentylidene ketal, which is right here, right? And again, if you think about the chemistry behind this is organic two, like late semester organic two, where we learned about like making acetals and hemiacetals. So you normally, to make an acetal, you would add two equivalents of an alcohol to a carbonyl, right? So adding acetone here, or adding acetaldehyde here, or adding this cyclopentanone here, that's how you're able to protect these diols as acetals or ketals, right? Same thing here, right? You would start with the cyclohexanone and react it with the diol, and it's like a condensation type reaction, so it's very straightforward chemistry. Um, the benzylidine is also another popular acetal protecting group, and you just use benzene. I'm sorry, benzaldehyde plus the diol, and that'll give you that benzylidine acetal. All right. So again, this is the general method for protection, right? You can see for the acetonide, you can just add in acetone, or you can start with the dimethoxy acetal here, which comes from uh, treating acetone with two equivalents of methanol, right? You can add that, and it acts the same way because this dimethoxy group is basically just a masked ketone anyway. So you can, and so the chemistry is basically the same, right? Um, it just goes through like an elimination where you do a proton transfer, then an elimination, and then the addition. So it's basically addition, elimination to swap out both of these groups with the two diol groups right here, right? Or you can use a like a enol ether, and um, you'll get the same outcome because again, this is again like a masked version of the acetone. It's the enolate, the methoxyenolate of acetone. So it's the same type of chemistry. All right. And if you want to remove them, then normally it's like some type of acidic cleavage to take off the acetonide. You can do some type of acid, some acid source, or you can use like a Lewis acid and a hydride. So you can use something like red al or dibal or some uh, Lewis acidic hydride donor. And then here you can see that you can selectively with those types of deprotectant agents. You can see that you can selectively remove um, the acetonide to free up one of your alcohols. Right? There's no ratio here because more than likely you get both products. And then you could use an oxidizing agent as a deprotectant. And then if you look here, you get the same thing. You get like a beta hydroxy carbonate species like here. And there's again competition. So there's no ratio. You probably end up getting both products. And you can separate them out probably chromatographically. If you have these two products, especially here, when you get these two diastereomers, then you could probably separate them out chromatographically. All right. So here you can see where you have this again selective protection, deprotection. You can see right here that you get the 1,2 diol protected in a 5-to-1 ratio when you compare it to the 1,3 diol, just treating this with acetone and toxic acid, right? So the 1,2 diol is right here. And then if you treat that with just acetone and toxic acid, you're going to get the acetonide. And then the 1,3 diol is here, right? You can see that motif over here as well. Um, so yeah, again, the strategy and the selectivity is, it's up to you what you're trying to do in your synthesis. And you can see here it's in a 5-to-1 ratio, and all your chirality is maintained. So these two chiral signals are maintained. So what you're able to do in this case, these two are enantiomers, so you wouldn't be able to separate them chromatographically. But if they were diastereomers, then you could separate them chromatographically. Uh, but for enantiomers, you have to do like a resolution, like a kinetic resolution or something like that, to separate those two species away from one another. All right. Um, yeah. So here again, this is another example of a selective protection. Right. You have this triol, and again, you have a 1,2 motif and a 1,3 motif. And with zinc chloride and benzaldehyde, you're able to protect uh, the 1,3 diol over the 1,2 diol and leave this free, right? And this is a part of this was done by Frakowski, and then you over here you can see that this fragment is a part of a larger molecule. So right here, this is uh, uh, lampteroflavin. It's a bioluminescence agent, and this is done by Asobi. And you can see right here, you have a TROC protecting group that's on here, and you have a 1,2 diol here and a 1,3 diol here, right? So to protect that 1,3 diol, right, you use the methoxy. Uh, Let me go back, make sure I call it the right thing. I don't want to not call it the proper name here. The methoxybenzylidine acetal. So that's what that is, that 4MP right here. So this is a methoxybenzylidine. You treat this product right here with that in PPTS and DMF room temperature, you get a 96% yield. And this is, again, highly efficient, and none of your other functionality gets disturbed, right? And you're able to treat that 1,3 diol and protect it. And if you look at the final product, which is right here, right, you end up deprotecting that alcohol, that diol, and having it free. But there's some other chemistry that happened back here where this TROC group is. You can see that oxygen ends up as a part of this heterocyclic system right here, right? All right, so let's see. Let's look at one more example, and this is an example of a selective deprotection, right? You can see that you have a 1,2 diol here and here, and treating this at 80 degrees Celsius with acetic acid uh, and water, you can deprotect this 1,2 diol over this 1,2 diol. And it's probably, again, related to sterics, because this 1,2 diol is a little bit more sterically encumbered. It's got more functional groups around it, and this one is a little bit more open and easier to access, more accessible. So that's probably why you see this one being deprotected selectively. And the same thing here, where you